Hi everyone, my name is Marissa Lo and I'm a final year PhD student at the University of Manchester. You might remember from my previous VMSG talks that I usually work on lunar volcanism, but today I'm going to talk about something slightly different, using experiments to investigate gas flow through a magma analogue. This project was the brainchild of my supervisor Mike Burton and Ed Llewellyn at Durham, with the experiments completed by myself and Ed's PhD student Ariane Loisel. So I spent a couple of weeks in Durham in the summer of 2019, completing some analogue experiments, which Ariane then followed up with some rheometry experiments. So I'm very excited to be presenting about something that's been in the works for a couple of years. And as someone who usually just stares at MATLAB and models on their computer, this made for a very refreshing change. So the rationale behind this work was to investigate how gas can decouple or flow through magma in order to produce passive degassing at basaltic volcanic systems. We know that passive degassing has a greater contribution to total emissions compared with eruptive degassing at several volcanic systems such as Etna or Stromboli. And we wanted to test one of the many hypotheses for gas decoupling and flow, in this case, gas flow through connected pathways. And a piece of work on fluid dynamics that piqued Ed and Mike's interest in particular was a 2002 paper by Kliak-Handler, which reported a chain of bubbles in Methacel, a concentrated polymer solution, a picture of which you can see on the right-hand side. You can see these centimetre scale bubbles that are connected at the top and bottom by what were called little necks. So the aims of this work were to see if we could recreate those bubble chains reported in that paper. Second, to constrain the different experimental conditions needed to produce the bubble chains. And third, to characterize the rheology of the fluid we were using. How similar was this analog fluid for magma to real magma? So in order to do this, we use hydroxyethyl cellulose, which I'll call HEC from now on, which is a polymer that dissolves in water to create a viscoelastic solution with a shear-thinning rheology. The HEC solution was made by mixing HEC powder with warm water, as shown by the pictures on the right. And once the solution had cooled, I poured it into a perspex pipe that was clamped upright. Into the base of the pipe, I then connected a gas injection nozzle where I could control the gas flow rate with a flow meter. The one in the picture on the right went from 0 to 0.5 litres per minute, and for each experiment run, I incrementally increased that gas flow rate and made any notes on observations of how the gas or bubbles were flowing. So there were 4 variables in the experiment overall: the gas flow rate, the HEC solution concentration, the size of the pipe, and the size of that gas injection nozzle. For the rheology, this was characterized using a thermoscientific rheometer, using a combination of rotational and oscillatory rheometry, using strain rates between 2 and 150 pascals. When I completed the gas flow experiments, I kept aside a small amount of the solutions for Ariane to test, and she then collected data on the apparent viscosity, shear-thinning rheology, and viscoelasticity of the HEC solutions. So on to some results from the gas flow experiments, which I'll show you using some videos. Apologies in advance for flickering in the videos. I reduced it as much as I could, but if you are sensitive to flickering lights, please look away now. So as I said, for each experiment run, I increased that gas flow rate from 0 to 0.5 litres per minute, and it observed 5 distinct gas flow regimes. The first was separate bubbles, the sort of thing you would expect to see if you were blowing into, say, water with a straw. Each bubble formed at the nozzle, broke off, and rose separate to any other bubbles. However, as I increased that gas flow rate even more, you'll see that in the wake of this bubble here, you're starting to get a connected chain of bubbles. And I'm just going to swap to a different video to show you this more clearly. So here you can see in the wake of an individual bubble, I have a chain here connected at the top and bottom with a narrow neck. And you can see the gas moving up through the bubbles. They kind of flicker, but that chain is mostly stable. As I increased the gas flow rates further, there came a bit of a transition point with a mixture of round bubbles and more elongate looking bubbles. You can see here the gas flickering up through them, but again, that chain is stable. It's staying in the same place each time. And then third, from those round bubbles, I noticed a transition fully into what I called the rice grain-like bubbles. So these were much longer, much narrower. They still had a clear neck in between them, so you can see separations there between them, but the shape had definitely changed. From that rice grain-like chain, I noticed a change into what I called a flue. So in this case, the necks between the bubbles weren't really visible, and it sort of looked like a pipe traveling through the solution. And then finally, as I increased that gas flow rate even more, that flue began to break down at the top into the individual bubbles once more. So just to summarize all of the different gas flow regimes there, from left to right, we have increasing gas flow rate. And this is for a 1.7 weight% HEC solution in a pipe that is 6.5 centimeters in diameter. And each of those black and white ruler markings is about a centimeter. So the scale isn't consistent, but it's just to show the features of each gas flow regime most clearly. So to move on to the rheometry measurements completed by Ariane, and this was sort of the final piece of the puzzle to put the experiments into context with real bubbly magmas. So the rheometry measurements found that the HEC solutions we used were viscoelastic and follow the Cox-Mertz relationship, which is where viscosity as a function of strain rate is equal to viscosity as a function of the angular frequency of oscillation, so during those rheometry experiments. And this is a relationship that real magma follows as well. So we combine the rheological data on HEC with data for real bubbly magmas using a tool created by Tom Jones, which was published in 2020. And we were able to fit quite well the 1.7 weight% HEC solution to a bubbly magma with a gas fraction of 0.6 and a melt viscosity of 1000 Pascal seconds. So just to summarize, quite a lot of work here. We produced bubble chains in 2 HEC solutions at 1.5 and 1.7 weight% concentrations over a fairly limited range of gas flow rates. And based on the different rheological properties of HEC, we do think it is a suitable analogue for magma. So we do conclude that bubble chains could form in real life magmas under the right conditions, so could be a mechanism for open system degassing. But there are lots of different future developments that could be made, such as incorporating crystals by putting small particles in the HEC and trying to explain the real life analogue of that gas injection nozzle at the bottom of the Perspex pipe. So thank you very much for listening, and I hope you enjoyed the talk, and I look forward to any questions. Thank you.